So hi everyone, I'm Ran, co-founder and VP engineering at Qwak, which is an ML engineering platform designed to enable data scientists and machine learning engineers to build, deploy, maintain, and monitor machine learning models and features in a single platform. And an integral and very significant part of that platform is the feature store, which I will focus on in this session. So first, agenda. I'll give a brief intro about the concepts and goals of a feature store and the set of problems this component is trying to solve. Then we'll go over reference architecture for feature store and the design principle such a system should include. And I'll do a short case study afterwards, meaning a usage example with the concepts I'll introduce. So let's start. So what is a feature store? Okay, there's quite a lot of ways to define it, but I'm particularly fond of the following one. A feature store is a data platform for machine learning that facilitates the discoverability, reuse, and accuracy of features across an organization. And I like this definition because it highlights the hard problems feature store is trying to solve. And I'd like to focus on basically two of them. The first problem is that features that can and should be shared across models are redefined over and over again by different data scientists or different teams. Okay? For example, the feature timestamps first transaction can and should be reused for different types of models. For example, an LTV model, a lifetime value, churn prediction, or fraud detection. The second problem, which engineering-wise is the hardest one, is the inherent inconsistency between features generated for offline purposes, like model training, and online purposes, meaning model serving. And I'll elaborate more on that a bit later on. This is kind of a classic problem of data processes that from one hand are written in Python or SQL by data scientists, and on the other hand, in more backend-like languages like Java, Go, Python, and more for serving purposes. And that leads to a problem called training serving skew. Okay? The difference between model performance during training versus model performance during serving. And from these problems, we can derive the purpose or goals of a feature store, which is one, creating a single curated, discoverable source of truth for features on the organization level. Second, to enable reuse and collaborations of features between different models. And third, to systematically ensure the consistency between features generated for offline, aka training purposes, and online serving purposes. So now I hope that the motivation and vision are a bit more understood, and let's dive into how such a system should work, and basically the principles behind it. And the most basic functionality a feature store should implement, in my perspective, is basically a library of features. Again, the idea is to create a shared, discoverable source of truth, feature registry or repository where data scientists and ML engineers can just skim through and see the features that are already available for them to use. Second functionality is the transformation layer. Well, as I see it, transformation layer mainly enables ownership. Ownership of the data scientist or machine learning engineer on his feature pipelines. And by that, reducing his dependency on data engineers that otherwise, in many cases, just need to implement these transformations for him, for the data scientist. And a third layer is observability. Data observability is a very hot topic in the data engineering world, and for very good reasons. And in this context, the observability layers enables getting a snapshot of the health of the feature pipeline. Okay? For example, by creating alerts that notify on significant data changes, which can be expressed in a few very interesting places. For one, volume, data volumes that the feature set is processing, which may have jumped or dropped significantly. Second, distribution, significant variations of data distribution across ongoing executions of the features. And third, status of feature data, a feature that new data simply wasn't ingested to it for some period of time. And that sums up the first layer of the feature store, the feature management layer, which again includes the organizational feature library, enables discovery and exploration of features, the transformation layer itself, meaning the actual feature business logic, and the data observability layer, which includes a health view of the feature pipelines. And the second pillar is the materialization layer, the very heart of the feature store. Okay? Materialization, or to materialize, is the action which computes the data values, and if necessary, writes them to the storage layer, usually for fast or frequent access to them. And this is the component which deals with the hardest engineering problem, okay? The aforementioned training serving skew. And the main concept behind the materialization layer is single feature computation, okay? Meaning a unified data pipeline that is being used to generate data both for training and for serving. But what is the actual problem in different pipelines for training and serving? Okay? Let's look at this rather simple case. On the left side, we can see an SQL query, which computes the feature average transaction over the last week. And on the right side, same exact feature, just as a part of a serving flow, some production flow. And as I specifically learned the hard way, this discrepancy is very problematic. The feature rewriting process is simply too error-prone. And more often than not, implementations differ, okay? Leading again to training serving skew, difference between the performance of model during training versus the performance during serving. And the way to overcome that is rather straightforward. Single feature computation, which streams data to a dual database system. This is kind of the beating heart of the general feature store architecture, The first leg, the offline store, which should contain the current and historical feature values. This is a store, the system, feature store, queries to generate potentially large and wide data sets, usually not just for model training purposes. And for that reason, it's usually implemented on top of file formats such as Parquet, Hoodie, Delta Lake, and persisted on some object storage. The second leg is the online store, which is used by the serving flow typically to extract a single feature vector, but in production SLA, meaning in near real-time latency, usually in milliseconds. And for that reason, the online store is commonly implemented on top of fast key value databases. Redis, for example, is a classic candidate for that use case. And the third leg is real-time transformations. Okay? Not in all cases, features can be pre-computed, can be computed in advance. There are cases, and I'll show an example in the use case, where there is a need to perform basically transformations, feature engineering, based on data that is only available on the inference request itself. And for that purpose, the real-time transformations are designed for, basically. We can think about them as kind of a non-materialized features, which are only computed, which are only manifested on request, upon request. And this structure, this diagram, solves the training serving skew problem by the basic fact that there are no more separate pipelines, okay? But one pipeline, which is what we're seeing here, streaming data for both purposes, training and serving, to the offline and online store corresponding. And the last part of the system is its APIs. The first API is for model training, generating potentially large and wide data sets from the offline feature store. And the second API is for serving purposes, okay? Retrieving a feature vector for scoring purposes in very low latency, milliseconds usually. And it's important to emphasize that even though the stores are different in technology, different by design, they are both fed from the same data source of truth, okay? Which is being generated by the transformation layer. Important note. And as a summary for this part, let's connect the purposes of the feature store with the diagram I just showed you. So the source of truth and feature collaboration are solved or implemented by the management layer, specifically the features library. And the training serving skew is eliminated by the materialization layer, okay? The unified data pipelines, which ingest data to the offline and online stores. Okay, so let's now build a short usage example for the feature store we just defined and try to connect the dots. And this is the data set we'll work on, okay? Transactions. The data set contains, as you can see here, the user ID of the transaction committer, its amount, location, and time. And the model we'll use for the example is a classic one, fraud detection. We would like to classify whether a transaction is fraudulent or not. And we have three data sources which are relevant for our use cases. One, the historical transaction table stored in Snowflake. Second, the live transaction stream, top of some Kafka topic. And third, the suspected transaction itself. Okay? More specifically, the properties that are a part of the fraud classification request, properties themselves. And these are the features we're going to build. Okay, for batch features, average and standard transaction per customer, again, we'll build them on top of the Snowflake data. Streaming feature, last transaction amount and time on top of Kafka, and feature based on the invocation data itself, time since last transaction and T from average transaction amount. And we will build them on top of an SDK, which is a subset of Qwak's feature store SDK. Let's start with the definition of a batch feature set. So a feature, or actually a feature set, family of features, has a name, right, which I can later look for in my features library. It has a data source, in our case, the transactions table from Snowflake, a scheduling policy, which sets the intervals between executions of the feature set transformation, the actual logic itself, a validation parameter, which is an addition I like very much, and kind of connects to the data observability domain. As you can see here, it contains a set of data validation using a very cool library called Great Expectations. And the main idea here is to build some kind of a defense layer around data coming into the feature store. In this case, we're running max and min validations on one of the columns of the Snowflake table. And the last parameter is the transformation itself. A rather simple query, which computes the average and standard deviation of a transaction. Okay, so now we are done with the batch feature set. Let's add streaming. And this is the streaming feature set. The main difference here is the data source. In our case, the data source is the stream of transaction coming from a Kafka topic named Kafka transactions. And on top of that topic, we're running a streaming SQL function. You can see it extracts the last transaction amount and time. And the last feature set we're going to implement is the real-time feature set. And the idea here is to calculate feature based on data available only on the prediction request itself. In our case, properties which are a part of the suspected transaction, which I would like to classify. Okay, so let's kind of connect all the dots. Okay, and see the flow of a prediction request using the feature store. So on the upper left side, you can see the batch features computed from Snowflake and ingested into the online feature store based on some schedule. And below them, the streaming features, okay, computed based on a Kafka transaction stream. And when an invocation request is coming along, see that again in a second, it is passed to the feature serving platform, going through the real-time transformations, okay? Going through the real-time transformations, and the relevant data is extracted from the online feature store and returned back to the model for prediction. And you can see that the entire left side is completely independent from the invocation request. Okay? New data is constantly being ingested into the online feature store. Okay? The two flows, invocation flow and ingestion flow to the feature store, are completely independent. So thank you very much. And if you are interested to learn more about the concepts or ways to implement such a system, so feel more than free to reach out. Or if you are more into building systems like the one we just saw, we are always recruiting developers to join us and take part in designing and building Qwak's feature store. So thank you very much.